So 11.2 is an introduction to the infinite series. Really, the infinite series is going to be the whole point of this whole chapter, but so therefore I disagree that that's a good name for this section, because there's going to be more sections about series than just this one, but that's what they called it in the book, at least. Okay, so of course, it makes sense to talk about the sum of two numbers, like a1 plus a2, right? Now, if you wanted to talk about the sum of three numbers, well, that you can make sense of as well. You just need to take the sum of the first two and then add the next one to that. And then if you want four numbers, you just take what you found before and then add on a fourth term, and so on, right? So you can add up as many numbers as you want in this way. Okay? We just keep repeating this operation of addition, and in fact we don't even need these parentheses because by associativity of addition, well, they're all the same, right? Okay, so the sum of finitely many numbers, that makes sense. Now, what if you were to ask about the sum of infinitely many numbers? Well, that one is a little more strange, and so that's what we're going to get into today. Now that you know what a limit is, based on Calculus 1, we can actually talk about what we might mean by the sum of infinitely many numbers. So, let an be a sequence of real numbers. First thing we need to do is define what we mean by a partial sum. So, given a positive integer, let's call this positive integer k, the kth partial sum of the sequence an this is the value, which is often called sk. It's just the sum of the first k many elements of the sequence. Okay? So for example, if I give you a sequence that looks like, let's say A is the sequence 1, 2, 3, 4, 5, 6, and so on, we can talk about partial sums of this. The first partial sum is just A1, which is just 1. The second partial sum is A1 plus A2, which is 1 plus 2, and that's 3. The third partial sum, A1 plus A2 plus A3, which is 1 plus 2 plus 3, and that's 6. The fourth partial sum is 10, the fifth partial sum is 15, the sixth partial sum is 21, and so on. Okay? So we're just adding up the first few elements of a sequence, and we're calling that a partial sum. Okay? But now let's notice here these partial sums themselves form a sequence, right? They themselves form a ordering of infinitely many real numbers, right? And so what happens if we take the limit of all of those partial sums? Well, that is what we mean by an infinite series. So, let an be a sequence of real numbers and I guess I don't really want to say this the way I'm saying it in my notes. I need to correct that. And let SK, SK is going to mean the kth partial sum of the sequence AN. Now, if this new sequence SK converges to a real number let's call this real number S, then we say that the series sum from n equals 1 to infinity of AN converges to S and that S is the sum of the series. Okay. On the other hand, if no such real number exists, then we just say that this infinite series is divergent. So, if no such real number exists, the sum from n equals 1 to infinity of AN is called a divergent infinite series. Okay? So, just to emphasize, you give me a sequence AN. What you mean by the infinite series n equals 1 to infinity of AN this means the limit as k approaches infinity of the kth partial sum of AN, which in turn means the limit as k approaches infinity of the sum from n equals 1 up to k of AN. Okay? So it's a limit of just a different kind of sequence now. So, for the first part of this chapter, we're mostly going to be concerned with infinite series whose terms are all positive. Now, you might be thinking, well, you take infinitely many real numbers that are all positive, you add them up, the answer is just going to be infinite, right? Not necessarily. Okay. Let's just consider the following. There was a Greek philosopher named Zeno who felt the same way. He took issue with this notion of infinite series. It wasn't called infinite series back in his day, but well, it was that kind of idea. That kind of adding up infinitely many positive numbers and getting a finite result. Well, let's see here. So Zeno did a thought experiment that went kind of like this. Let's say we have 1 unit of length here, and this unit can be whatever you want. You can make it a mile or a meter or a nano angstrom or whatever. Just 1 unit of length. Okay? And let's suppose that what you want to do is you want to move from here over to here. And let's say you want to do it at 1 unit per second, or whatever unit of time you will want. Okay? So presumably it would take you 1 second to get from here to here, right? Or 1 hour, or whatever kind of unit of time you're using. Let's say seconds. It'll take you 1 second to get from here to here if you move at 1 unit per second. Okay? But now, if you wanted to do that, if you wanted to move from 0 to 1, well, first you'd have to move from 0 up to 1/2. Right? You can't get from here to here without going through 1/2 first. Okay, and so that's going to take you 1/2 of a second. So then your goal is to get from 1/2 to 1, right? Okay. Well, if you want to get from 1/2 to 1, you're going to have the distance between yourself and 1 once again, so you'll get to 3/4. Okay, and that's going to take you 1/4 of a second. Right, because you're moving from 1/2 to 3/4, that's 1/4 distance, so you're moving at a speed of 1 unit per second, so that's going to take you 1/4 of a second. So then you're at 3/4, and then you want to get to 1. Well, again, you're going to have the distance between yourself and 1, right? Okay. Let's see, 3/4. The distance between 1 and 3/4 is 1/4. You have that, you get 1/8. And so then what you want to do is you want to get to 7/8. And in going from 3/4 to 7/8, well, that's going to take you 1/8 of a second. Now, in order to get to 1 from 7/8, you're going to have the distance between yourself and 1 once again, right? You're going to have to, let's see, the distance between 1 and 7/8 is 1/8, so to have that you get 1/16. So you need to move up to 15/16, which is like right there. And that's going to take you 1/16 of a second. You see where this is going? You're going to have to keep having the distance between yourself and 1 over and over again, literally infinitely many times, right? So how much time is that going to take you? Well, it's going to take you the sum of 1 over all the powers of 2. So this is what we mean by the sum from n equals 1 to infinity of 1 over 2 to the n. So Zeno, he said to himself, all right, in order to get from here to here, you need to accomplish infinitely many tasks. You need to halve the distance between yourself and one infinitely many times. And each of those tasks is going to take a finite amount of time, right? So, Zeno asserted that since he reasoned that it was impossible to complete infinitely many tasks that all take a non-zero amount of time, he said, okay, motion doesn't exist. Which, okay, I mean, I guess you can believe that. He was basically claiming that motion was some kind of illusion, and that it doesn't actually happen, and there's something wrong with the way that we're perceiving the world. Which, I mean, I guess you can believe that. Or maybe that's just one. Okay? So, if you refuse to accept the idea of an infinite series, then you're going to have to admit that motion doesn't exist. Which, again, I guess you can do that, but you might find it difficult to talk to people. The other thing that I want to point out is you deal with infinite series all the time, you just don't realize it. Let's think about, for example, 1/3. 1/3, let's see. If you were to type this into a calculator, it's going to give you something like 0.33333333, and so on, right? And it's not going to keep going because the calculator has a finite, it has a limited display, right? Can't just keep displaying digits forever. So it's going to round for you. It's not going to display all of them because there are literally infinitely many of them. So instead we think of this as 0.33333 repeating. Okay, it's a repeating decimal. Now, literally what this means 0.3 plus 0.03 plus 0.003 plus 0.0003 plus ... And by the way, that means 3/10 plus 3/100 plus 3/1000 plus 3/10,000 and so on. Okay? And this is exactly what we mean by the infinite series sum from n equals 1 to infinity of 3 times 1/10 to the nth power. Again, if you want to believe that these two things aren't the same, I won't stop you. I can't stop you. But you might find it difficult to make friends. Okay? So, infinite series, they're actually not that outlandish. As long as you're willing to accept that sometimes we humans do infinitely many tasks in a finite amount of time. Okay, so let's start with one of the most important types of infinite series. So, definition. So, here's just one type of infinite series that could happen. A geometric series is an infinite series that looks like the sum from n equals 1 to infinity of an, where an is a geometric sequence. Okay. And we talked about geometric sequences in the last lecture. That was just any sequence whose terms, the successive terms multiplied by a constant factor that we called r, right? Now, since every geometric sequence looks like an equals constant times r to the n, every geometric series is going to look like the sum from n equals 1 to infinity of constant times r to the n. Okay? For some appropriate choice of b and r. Now, let's ask a question. First of all, let me just point out, both of these series that I gave as examples, this one here, which is I guess it's 1, and this one here, which is 1/3, these are both called geometric series because they're both a constant raised to a power times some constant. This one is 1/2 raised to the n times 1, and this one is 1/10 raised to the n times 3. Okay, so they're both geometric series there. So, question. Do all geometric series converge? These two sure do, but does every geometric series converge? Well, let's see about that. So here's what we're going to need to do. First of all, consider the geometric series sum from n equals 1 to infinity of b times r to the n minus 1. Okay? Every geometric series can be written like this. You might be a little bit concerned why there's an n minus 1 rather than an n, and that's because you can change the form of it in order to make it look like that. Because note that this is exactly the same thing as the sum from n equals 0 to infinity of b times r to the n. Okay, so those are the same thing. All right, so we have a few cases that we need to consider here. So if r equals 1, then, well, that would mean that sk, the kth partial sum, well, that's the sum from n equals 1 to k of, let's see, b times 1 to the n, okay? 1 to the n, I'm pretty sure, is just 1, so this is just b over and over and over again, right? So, this is k copies of b all added together, which is exactly what we mean, what we mean by kb, right? K times b. So now, the limit as k approaches infinity of sk, the limit of the partial sums, which by definition is what the sum of the series is, this is the limit as k approaches infinity of k times b. So as k approaches infinity, this is going to approach either positive infinity or negative infinity, depending on whether b is positive or negative. And then I guess also if b is 0, then it just approaches 0. But this diverges unless b is 0. But of course, if b is 0, then this whole series is just, sum from n equals 1 to infinity of 0. And then that's just 0 added to itself infinitely many times, which is 0. Okay? So in that case, you wouldn't even really care about that series. It wouldn't really be that interesting in the first place. Okay? So what we're seeing here is that if this common ratio is 1, then this series diverges. Because by definition, the series is the limit of the partial sums. Okay? Now, let's see. What if r is not 1? Well, first of all, if r is not 1, then the kth partial sum is, well, by definition, that would be the sum from n equals 1 to k of br to the n minus 1 which in our case is going to be, let's see, b times r to the 0, so that's b, plus b times r to the 1, so that's br, plus b times r to the 2, so that's br squared, dot, 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 all the way up to br to the k minus 1 power. Now, let's just think about this for a second. So this is sk. Now, what happens if you multiply sk by r? Well, if you do that, r times sk is now equal to br plus br squared plus br cubed plus dot, 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 all the way up to br to the k. Right? But now, if you look at this looks an awful lot like this, doesn't it? It looks like all we did when we multiplied by r is we just added another term and subtracted off the first term. And so what we get here is that r times sk, this is actually the same thing as sk plus br to the k minus b. All right, and then what happens if we solve this for sk? Well, we'll get r minus 1 times sk is equal to b times r to the k minus 1. And therefore sk is equal to b times r to the k minus 1 divided by r minus 1. And it's okay to say that because, again, r is not 1, so we don't have to worry about dividing by 0 here. Okay, so that's pretty nice. That gives us a formula for every partial sum of a geometric series. Now, let's think about if we take the limit of this. Let's see here. We want the limit as k approaches infinity of sk, because that, by definition, is the sum from n equals 1 to infinity of b r to the n minus 1. So by this formula that we just figured out, this is the limit as k approaches infinity of b times r to the k minus 1 divided by r minus 1. Now let's think about that for a second. What does this approach? If you're saying infinity, then you're right as long as r is greater than 1. If r is not greater than 1, this will not approach infinity. If r, first of all, if r is something like 0, well, first of all, you wouldn't care about this series much because, again, it's just 0. But in that case, this would not approach infinity, this would approach 0. But even if it were something like 1/2 raised to an exponent that's approaching infinity is also going to approach 0. Okay? So what this converges to, or fails to converge to, will depend entirely on what r is. So, if r is between -1 and +1, it converges to b, or b over 1 minus r. So, if -1 is less than r, and that's less than 1, then this converges to b over 1 minus r. And I'm getting that by just saying, okay, this is 0 minus 1, so that's -1. Negative b divided by r minus 1 is the same as b divided by 1 minus r. Just canceling the negative sign from the top and bottom. Okay? And then if this is not the case, it's going to be divergent. Okay? And so we have the following theorem. Let's just summarize all of this stuff in a theorem. So, let b and r be real numbers. First of all, if the absolute value of r is greater than or equal to 1, then the sum from n equals 1 to infinity of br to the n minus 1, the geometric series, diverges. On the other hand, if the absolute value of r is less than 1, which is what we mean when we say r is between -1 and 1, if the absolute value of r is less than 1, then the geometric series n equals 1 to infinity br to the n minus 1, this is actually equal to b over 1 minus r, and therefore convergent. All right? So this is great. This completely characterizes all geometric series. Every geometric series, you just need to, first of all, realize that it's a geometric series and find its common ratio. Once you have that, you'll know if it's convergent or divergent. And if it's convergent, you'll know what it converges to. Okay? Trying to fix the lighting here, but it's not working. Oh well. All right, so that's going to be a very helpful theorem if we ever encounter geometric series in the future. Wink, wink. But not all series are geometric. So what happens if you have a non-geometric series. Well, it depends. Some series are far harder to deal with than others. The geometric ones are pretty much the easiest ones. Now, another easy kind is called the telescoping series. So, some series, not geometric ones, but some particular series are called telescoping series. Which have terms that cancel pairwise. Okay, let's look at an example of what this looks like and how to deal with it. So, we want to determine whether this series is convergent or divergent, and if it's convergent, we want to find its sum. So, determine whether the sum from n equals 1 to infinity of, let me get this right, 1 minus n over 1 minus n plus 1. No, I said that wrong. I said minus as divides it. Never mind. Whatever. Determine whether this converges or diverges. And if it converges, find its sum. So the way to handle this kind of series is we got to write out the partial sums and see what that limit will approach. Pretty much the same as the geometric series. It's just, well, it's going to have a very different behavior now. So by definition, the kth partial sum is the sum from n equals 1 up to k of 1 over n minus 1 over n plus 1. Now, at first that doesn't look great. That doesn't look like it'll be easy to deal with, but let's write this out in a different way. This is 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 and so on, all the way up to, let's see, second to last term is going to be 1 over k minus 1 minus 1 over k. Last term is going to be 1 over k minus 1 over k plus 1. Sorry, ran out of space there, got a little bit sloppy. Alright, now, let's just examine what we're looking at here. Correct me if I'm wrong here, but I'm thinking this negative 1/2 cancels with this positive 1/2, and this negative 1/3 cancels with this positive 1/3, and this negative 1/4 is going to cancel with the 1/4 that appears in the next term, and then this 1 over k minus 1, that's going to cancel with something that appeared in the previous term, and then negative 1 over k, that's going to cancel with 1 over k. So all of this stuff cancels. The only thing that we have left is 1 over 1, which is just 1, and negative 1 over k plus 1. And that's the kth partial sum, right? So, by definition, the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1, well, by definition, that's the limit of the partial sums as k approaches infinity. So that'd be the limit as k approaches infinity of sk, which in our case is the limit as k approaches infinity of 1 minus 1 over k plus 1. Now as k approaches infinity, k plus 1 of course also approaches infinity. And then this denominator gets larger and larger, so this whole fraction shrinks. And so what we get here is that this sum is in fact 1. Okay? And pretty much every telescoping series works like this. In some way, you've got to write it as function involving n minus function involving n plus 1. And then make sure a bunch of things cancel. Sometimes, in this case, only the first and the last term survived and everything else canceled, right? Sometimes there are more terms that can survive. That can also happen. But basically, they follow this same kind of flavor. Okay. Now, I'm going to tell you something that I think maybe I'm not supposed to tell you. Nonetheless, I think it's important information for you to know. So here we have geometric series and telescoping series, right? And so we just figured out how to work with these two. We have this nice theorem for finding the sum of a geometric series if it converges. And for a telescoping series, we just have to look at the partial sums. Every other series in this class is going to be too hard for us to actually figure out the sum if it converges. Okay? In general, you just give me any old infinite series and you ask me, figure out the sum of this thing. Let's say it is convergent. Figure out the sum of this thing. That can be an insanely difficult question. Really, really difficult. Okay? So, for this class, the only series that you're going to be concerned with their actual sums is geometric and telescoping series. Okay? And maybe when we talk about functions being written as power series, you'll be able to work with those too. But these are the main ones, telescoping and geometric series. Other than that, you're not going to be able to find the sum. It's just going to be too hard. Okay? So then the question becomes, okay, then what the hell is the rest of Chapter 11 about? The answer is, well, it might be too hard to figure out what the sum is if you know the series is convergent, but what's not too hard, still hard enough to be in the class, but not too hard, is trying to figure out whether a given series is convergent or divergent. Just figure out whether it's convergent or divergent. If it is convergent, I just want to know that it's convergent to something. I don't necessarily want to know what that sum is. Okay? And so the bulk of Chapter 11 is going to be devoted to solving that problem. Now, in order to figure that kind of question out, we're going to have several theorems that are going to help us test whether a series is convergent or divergent. And the first, and maybe the most important one, is this one. So this theorem is called the test for divergence, which I think is a really lame name for it because, you know, all of these tests are tests for divergence. I've also heard of it called the nth term test and the general term test, but yeah, this book calls it just test for divergence. Here's how it goes. If the sum from n equals 1 to infinity of an is convergent, then the limit as n approaches infinity of an must be 0. Okay? So let's look at a few examples of how this works. So we're going to look at, we're going to ask whether this thing is convergent or divergent. And if it is convergent, we're going to find its sum. Although based on what I just told you, we're not really going to find its sum. And so that means we're going to show that it's divergent. So this one is the sum from n equals 1 to infinity of n squared divided by, let's see here, n squared minus 2n plus 5. I guess that actually ends with a question mark. Okay, so determine whether this thing is convergent or divergent. The first thing I think of whenever I see a series and you ask me, is this thing convergent or divergent, I think, okay, is it geometric? And then if it's not, then I think, okay, is it telescoping? And if it's not, then I think, okay, does the test for divergence show that it's divergent? So here's how you would figure that out. Let's examine the limit as n approaches infinity of the nth term of this series, which is n squared over n squared minus 2n plus 5. I want to know, as n approaches infinity, what does this approach? Well, we can divide top and bottom by n squared, just like in Calculus 1. So then this becomes the limit as n approaches infinity of 1 divided by 1 minus 2 over n plus 5 over n squared. Now as n approaches infinity, both of these fractions, which have n in the denominator, are going to approach 0, because their denominators will just continue to grow without bound. And so this is 1 over 1 minus 0 plus 0, so that would make 1. Okay, now let's think about what we just discovered here. We just discovered that the terms of this series, not the series itself, but the terms of the series, are approaching 1. Also, the test for divergence tells us that if the series is convergent, then its terms approach 0. What does this mean? It means this thing can't be convergent. Okay, so since this limit is non-zero, the test for divergence indicates that the series is divergent. And by the way, I just thought of a point that might confuse people, so I should mention it, just to get rid of that right away. The terms converging as a sequence is a very different concept from the whole series converging. Okay? Yes, it's true that these terms approach 1, but that doesn't mean the sum of those terms is approaching 1. In fact, according to the test for divergence, it's not approaching any finite number. Okay? So test for divergence, we can use it by saying, all right, well, if this thing were to be convergent, then the limit of its sums, the limit of its terms would have been 0. It's not? Oh, well then in that case it's divergent. Okay. Let's do another example. So this time, it's the same question. We're going to determine whether this is convergent or divergent. This series, though, it's going to be the natural log of n. When n equals 1 to infinity. Okay. Well, again, it's not geometric and it's not telescoping. So let's see if the test for divergence can tell us anything. Well, if you take the limit of the terms, the limit as n approaches infinity of ln n, that's infinity, right? And I'm pretty sure infinity is not the same thing as 0, right? So the test for divergence is saying if this were to be convergent, then the limit of its terms would have been 0. Since it's not, that means it can't be convergent. So, by the test for divergence, the series is divergent. Let's look at another example. Same question. We're going to determine whether it's convergent or divergent, and if it's convergent, we're going to find its sum. This one is sum from n equals 1 to infinity of sine squared of n pi over 2. All right, well, let's see here. The limit as n approaches infinity of the sine squared of n pi over 2. Let's see. If n is an even number, then the sine squared of n pi over 2 is going to be an integer multiple of pi, in which case the sine of that is just going to be 0. On the other hand, if n is an odd integer, then n pi over 2 is going to be an odd multiple of pi over 2, in which case sine of that is going to be either 1 or negative 1, so then sine squared of that is going to be 1. All right, so it looks like as n approaches infinity, we have that oscillation problem. This just keeps going back and forth between 0 and 1, right? It never converges to either of them. So this one does not even exist. And once again, test for divergence says, all right, if you want to be convergent, you've got to have a limit of your terms being 0. And nothing is not 0. Okay? So, by the test for divergence, the series is divergent. Okay? So, what are we seeing in these examples? Well, we're seeing that the test for divergence works like this. If you have an infinite series and the limit as n approaches infinity of its terms is not 0, then the sum from n equals 1 to infinity is divergent. Okay? That's a restatement of this theorem, and it's pretty much how we always use it. Now, in math, a lot of statements take this form. They say, if you have this situation, then this thing happens. Okay? Now, for every statement that does that, every statement that looks like if, hypothesis, then conclusion, there's an associated statement called the converse. Okay? The converse of this statement is like if the sum from n equals 1 to infinity of an is divergent, then the limit as n approaches infinity of an is not 0. Okay? So that's the converse of the test for divergence. Right? Now, I just want to show you something. Let's think about this for a second. If a statement is true, does that mean that its converse is true as well? Maybe. Right? Let's see here. If my name's Mark Sullivan, then I'm the instructor for Math 142 V for the fall of 2020. That's true. And then if I'm the instructor for Math 142V for fall 2020, then my name's Mark Sullivan. Okay, so that's a situation where a statement and its converse are both true. What about the following statement? If a quadrilateral is a square, then it is a rectangle. The converse would be the old switcheroo of those two premises. The converse would be saying, if a quadrilateral is a rectangle, then it is a square. It's true that if a quadrilateral is a square, then it's a rectangle, but it's not true that if a quadrilateral is a rectangle, that automatically makes it a square, right? And so what you see here is that the converse of a true statement might not be true. And in fact, an enormous amount of mathematics is dedicated to trying to work around the fact that the converse isn't always true. So here, is the converse to the test for divergence true? If a series is divergent, does that mean the limit of its terms was non-zero? No. This is false. Okay? For example, the harmonic series. We talked last lecture about the harmonic sequence. I just mentioned it. It was the sequence of 1 over n, right? As n goes through all the positive integers. Yeah, the harmonic series is just, take all those and add them up. So n equals 1 to infinity of the harmonic series. let's see here. The limit as n approaches infinity of 1 over n, that definitely is 0, right? However, this is divergent. Okay? And why is that? Well, it's actually probably pretty hard for you to see right now. If you think about this for a while, you think like, wait, shouldn't that actually be convergent? I mean, you keep adding smaller and smaller things, right? You're approaching 0 as the n approaches infinity, right? Shouldn't it be convergent? No, it's not. So this is not enough. We need something more. Okay? And how do we know that this thing is divergent? We'll find out in the next lecture. Okay? So for now, that's it for today. Homework is up. Go ahead and get some practice on that.